Hi again, I'm Patrick Mannion, founder and director of content for Clartech LLC and president of TechWire International. I've been analysing embedded industry technology and trends for over 25 years, and I'm very excited today to moderate this particular panel entitled Spark ADA Journey to Adoption with NVIDIA, and it's basically about its decision to go with AdaCore to implement Ada and Ada Spark. Just a quick introduction again. As software becomes more complex, the chance of human error greatly increase, opening up potential for security and safety risks. NVIDIA is working with AdaCore to implement Ada and Ada Spark programming languages into certain firmware elements to reduce this potential error. In this webinar, you'll learn more about the combination of NVIDIA hardware with Ada and Spark and how it delivers robustness and security, improving efficiency and safety in the development pipeline. So with that, I'd like to introduce our two great speakers for today. To kick us off for roughly 15 minutes is Daniel Rohrer, VP of Software Security at NVIDIA. He'll give a quick overview of the business view and how NVIDIA came to formal methods for solving security challenges. After earning his master's degree at the University of North Carolina, Chapel Hill, Daniel got his relocation when he joined NVIDIA, working in a variety of technical and leadership roles ranging from kernel software, managed 3D and kernel development teams, creating NVIDIA's GPU software chip development, verification and process models, among many more roles. Finally, after 20 years learning about every part of NVIDIA's global business, he settled on his role as VP of Software Security. Like I mentioned, Daniel will speak for 15 minutes roughly, and then going deeper, we have Dhawal Kumar. Dhawal is Principal Software Engineer at NVIDIA, and after 18 years of experience doing software design and development in the areas of device drivers and firmware, Dhawal has also managed new GPU development from the software side and led development of a variety of new software and hardware features. More recently, he has been working on defining security architecture and development practices for firmware and hardware for NVIDIA's GPU product line. Dhawal holds a BTech degree from IIT Kanpur, India, and an MS from Stanford University in computer science. So we've got a great panel discussion today. So to kick it off, I'd like to turn it over to Daniel. Daniel, take it away.
Well, thank you, and welcome to all our guests today. Glad you could join us. Patrick did a great introduction. Been at NVIDIA for over 20 years. Definitely a new journey for all of us going forward. So I have a couple areas we're going to talk to today. Ada and Spark from the business side is really what I'm going to address and sort of how we came to the conclusion to go here. Dhawal will dive in a little bit more technically. Hopefully we can hit both sides of the audience interest here and make sure we answer as many of your questions about what we did here and hopefully potentially help you on your own journey to tackle these same problems as they apply to your local context. Just to orient a little bit for those maybe not as familiar with NVIDIA as a company, we supply computer components as well as full solutions into a variety of product verticals. And in particular, those verticals have a tremendous amount of security and safety risk that is certainly emerging against a bunch of macro trends. We'll talk about a bunch of those today. But as our complex systems carry forward into these various markets, it represents a real challenge in terms of delivering the right outcomes for those markets. We are in consumer electronic spaces, embedded, automotive, certainly autonomous, robotics, as well as medical and HPC data centers. And you can imagine the security and safety concerns of all those verticals are wide and varied, and certainly the challenges of delivering for all of those simultaneously tremendous. The result, NVIDIA, obviously who takes safety and security very seriously, has been looking at sort of the macro trends and asking, what can we do about this? Because certainly they're not good. And, within the scope of that, for all the markets that we're entering, there's a substantial increase in criticality of use, IP risk, pharma companies adding billions of dollars of their own data IP into cloud environments. Those infrastructure is obviously very sensitive, but as well life safety. When we look at medical and automotive, ISO 26262 and others, there's a very high degree of assurance that those product markets really want to see from suppliers like NVIDIA. They're very interested in the technique and methods of use of secure environments, and all of those play out here. Attacker trends, we have definitely observed here at NVIDIA that they are trending lower, and you can certainly see that in Black Hat and DEF CON type conferences that work in those areas that firmware and hardware attacks are on the rise. And when we translate that into physical spaces like autonomous vehicles where people can actually get at the hardware, it's not in a secure data center, the types of attacks that can be leveraged against your environment are all the more alarming. Likewise, ecosystem tooling to date really hasn't kept pace with the scale of attacks, nor have humans. The scale of attacks come harder and faster and more diverse. Humans and human-in-the-loop techniques are not scaling to meet the volume of attacks that we see today, as well increasing cost to update. In particular, when we look at firmware and hardware elements, taking a car off the road in order to make a software or hardware update is very, very costly. We want to avoid that sort of thing. But when we look at all of these trends, these macro trends driving risk, we're really challenged to say, how do we meet this? And what about our methodology today needs to evolve? And that really led to a number of questions about the status quo, about how we go about what we do here at NVIDIA, certainly in the security and safety context. And because we take it so seriously, we did what we normally do, which is, how do we tackle and break down hard problems? And, more importantly, what about this problem dynamic or these trends can we legitimately change to alter the outcome? Because the trends obviously were not good. And when we're faced with hard challenges, and NVIDIA as a company is pretty well known for tackling the hardest problems in the industry, we're not very shy about it, but we try to be very deliberate about it. And in that respect, we looked at first principles. What are the things that really drive the outcomes in this? And we settled on, 5 or so really critical factors that were affecting the outcomes here. In particular, we were looking at human factors. Certainly, secure code designers and security practitioners are super valuable resources within our organization, but they're hard to find. Just in the U.S. alone, there's a shortage of about 500,000 security practitioners industry-wide. It became very clear in our initial evaluation of these issues that hiring ourselves out of this problem was just not going to be an option. Likewise, I noted human timescales. When you're in a data center and code is submitted, checked in, tested, and shipped into production in less than 2 hours, finding a security practitioner, scheduling his time, and having him look at your code is just not tractable. And we needed other ways to augment our human capacity to go faster. And really the question was what strategies can we use to amplify the capital we have, because we couldn't acquire more security capital even if we wanted to. Led to other questions, the language and the fit that we use. We often look at process, methods, and tools when we ask these fundamental questions. When we looked at how we were developing today, that's typically C, C++ for these embedded in firmware spaces. And for the vast majority of it, they still suffer from, the decades-old challenges with that language. The spec of the language itself is ambiguous. There are lots of options left to compilers and implementers to have a variety of behaviors. There are many questions in terms of pointer chasing and taint analysis and things that bear on security concerns that are just not decidable, which means obviously the tooling that comes behind that does static analysis and others are limited. There are significant trade-offs between false positives, false negative rates. It adds a lot of noise. And even then, you still don't know when you're done. And fundamentally, we wanted to know, are we good? Can we answer that question? And the language and tool sets that we had today, at least in the C++ space, were very challenged in answering that even just basic question of particular concern to those businesses. Ecosystem support. Likewise, because NVIDIA has full solutions from ASIC up through cloud software with firmware, hardware, hypervisors, everything in between, you can imagine there's a diversity in the ecosystem that we really need to lean on to deliver those solutions. And as we got lower in the stack, the ecosystem really failed. There weren't a lot of off-the-shelf solutions in dynamic scanning and other spaces that could really supplement, which meant NVIDIA had to invest a substantial amount of internal capital to go build that ourselves. That capital is expensive. We'd much rather be spending it on the products themselves. What tools could we use to apply to bring us around to that? And then, getting again to the note on measurable, we like measurable outcomes. We like to be able to ship products into the field and know what the customer experience is going to be before they see it. Security is different that way. It's often proving negative. And one of the key challenges we've placed in front of the team is how do we turn this from a non-measurable, where we can't even answer, are we done yet, to a more measurable answer. And all of those solutions, presented, we swirled around this for a while, and we stumbled across, concolic methods for fuzzing and various other strategies. And the sort of basis around some of those other methods were formal provers. And we started asking questions. And, back in the day when I was going through college, formal provers were really just not a tractable problem for any code of any real scale. They were, interesting theoretical exercises. But as we pursued this question a little bit more, it became actually clear that there had been quite a bit of evolution in these spaces over time. So we posed the question to the team, what tools could we use? Could we fundamentally change? And it came back with a fairly heretical position, like, hey, what if we just stopped using C? And that raised a host of other questions, which effectively we carried forward and sort of started us on this adoption journey. In particular, like, how do we build a business case for this sort of heretical shift from the way embedded and firmware software had been done for decades? And I'm not going to lie, it's not easy building a case for this, but to the extent that we were successful, and Dhawal will certainly speak to the various successes we've had there, it has definitely been fruitful to be very deliberate about where we're taking the solution. But, fundamental questions to ask, how much are we actually investing? Moreover, how much do we need to invest tomorrow to meet those market demands? And all those macro trends really made the question, could we invest enough? Or, was it even possible to invest? As noted, we couldn't even hire the security professionals we wanted. Was the strategy we were on even possible? And I think we came back that it mostly wasn't possible, or if it was possible, that answer was somewhat suspect. So we went down this thing, and the question is, let's pick a solution. And we started looking at, what formal methods could we apply? And we stumbled across, I shouldn't say stumbled, we discovered Ada and Spark, the language, and AdaCore, the company who was promoting it, and really started diving deep. And while Dhawal will talk about some of the other languages we explored in this space, this is really the solution we landed on. And I'll describe a little bit why we landed there. First and foremost, the language type really picked sort of the partners that we would have to work with. But language, ambiguity, and decidability were really key aspects, right? Can we make formal proofs, stronger assertions against the language set to meet our integrity goals? And the answer out of the Ada and Spark side was yes. It had a compatible feature set with our target markets. It was linkable with C, which meant we didn't have to solve everything all at once. We could really pick targets that it was really worth that level of investment and go after those hard. Moreover, it had a credible ecosystem. There are many new and more boutique languages which are great. They are tools and useful for the purposes they serve, but it wasn't credible for us to bring into a safety certified market some of those other languages. They just weren't that mature. Ada has been around for decades, certainly from the 80s forward, has matured a lot, and layering in the Ada Spark layers really gave us a wealth of capabilities that we could rely on, not the least of which it has an upstream OSS presence. So even in the absence of a major player like AdaCore, we knew we could carry this forward into the future. And it was certainly welcome to have AdaCore as a responsive and willing partner to help us move forward in that way and bring their expertise to the table. We wanted an emphasis on provability over test and verify. Testing in security is pretty much impossible. And as noted, it's hard to know when you're ever done. We like the idea of moving efforts to the left in the design cycle. If your code compiles, it's doing generally the right thing if you've written your contracts appropriately. That's a great property for security professionals. It also generally means you're not finding things late in your cycle, which is deadly on program cycles. When you think about costs of updating, finding things late, especially, when you've got $1 million certification cycle with the NTSB and you want to deploy it in a car, that's really painful. We didn't like that property, and we were definitely looking for things that would discover these issues early, and Ada and Spark met that nicely. It also helps with scaling. As noted, I can buy machines. It's hard to find the experts that I want. But there are additional benefits that came out of that exploration, not the least of which is some of the overhead and testing and fuzzing and static analysis that we were doing wasn't necessary anymore because we could formally prove through direct means rather than indirect means of these other methodologies that this was done. And, the ability to repurpose those compute cycles as well as human capital to the core product was a huge benefit overall to the programs. And also responsiveness, call out to AdaCore team. we took on this program and we put it in a pretty tough corner. We were doing it at low-level firmware in a custom ASIC with registers and side effects that had to be modeled that were, sort of not uniform and not, generally their sweet spot. But the tooling, and through the course of the POC, and Dhawal will talk about this more, really lived up to that challenge, surprisingly so. We were expecting, there were definitely hurdles, but we were expecting, in some respects, to go through this POC and find out, no, we can't get there from here, and being rather sad about that. And in the end, we actually found rather a lot of legs in this. I guess going forward, having picked AdaCore, we really needed to find a target, and we really looked, as noted, to that low-level firmware and hardware interface for a variety of reasons. One of which is it's omnipresent, right? It is pretty much in every product, in every vertical that we serve. It's a huge footprint. So our ability to translate this strategy to those key areas could have a great deal of impact for the company. Most of those firmwares executed very high privilege, which means there's a large bang per buck for achieving improvements in this space. As noted before, attacker trends were shifting lower, and it's a high cost to remediate. Again, reaching out to the field to update firmware is a nasty business. It's not like, a Windows update that just sort of shows up every, Tuesday once a month. It takes a lot more infrastructure to drive that down. We are predominantly C development, so there was a rich set of targets in that firmware space to go. There are also smaller code bases, so we could do more targeted and tactical engagements, being less disruptive internally in terms of the engagement models to really move this strategy forward without upending, as I said, sort of the heretical statement of let's stop using C in this place. And moreover, it was aligned to customer concerns. We'd had a lot of concerns in light of, public events like Supermicro and others about the quality and security of the overall supply chain, which led to hardware and firmware questions writ large across the industry, across every vertical that we encountered. So it was a luxury to come back with an affirmative answer of a forward-looking strategy to address this, as well as making others in places like automotive safety certification folks who looked at us using formal methods as an additive benefit in terms of our overall product security and safety story there. So there are a lot of benefits going down this path. Just broadly outlining the business case and sort of how we came to the conclusion there. For many, it's not obvious, but if you're deliberate and find useful and desirable targets, it is, I believe, a sound strategy based on what we've learned for ourselves. Dhawal, I think, can go in a little bit more technical about the implementation of our strategy and the POC that we went through and give some insight in what we learned there. I will hand it to you, Dhawal. Dhawal, are you there?
Yes, Daniel. Just waiting to get the presenter right.
Yeah, I'm handing that over. Give me 1 second. Yes. Got it?
Yes.
Fantastic.
Thanks, Daniel. Once again, I am Dhawal Kumar. I work at NVIDIA as a principal software engineer with focus on security. As Daniel mentioned, I'll dive deeper into some of the technical aspects around NVIDIA's adoption of Spark. I'll cover 5 broad topics. First is firmware and their environment, which is essentially just a small extension of the last slide that Daniel showed. And what is Spark? What are the alternatives to Spark that we considered and rejected? The POC that we ran at NVIDIA for a few months, the conclusions arising out of POC, some of the concerns that arose along the way, and I'll end up with the key benefits of Spark and NVIDIA summary. Let's begin with the environment that surrounds the firmware. Daniel talked about firmware as a target that we picked, but what is it that we have within our firmware? What functionality do we have up there? This slide lists some of them. starting with secure boot. Next, we have DRM, which stands for digital rights management. It could be either games or video. We have video decoding, clock and voltage programming, low power transitions, and a lot more. And the first two are highlighted green since they are the most important, and we also chose a tiny portion of each of them for our POC. Now, where do these firmwares execute? They execute on so-called security processors, and we have two of them, or two kinds of them. First is Falcon, and the second is RISC-V. And when I say we, I'm referring to the GPU. Falcon is a proprietary NVIDIA hardware. It uses proprietary ISA, which means there wouldn't be any off-the-shelf compiler available for compiling, say, Ada or Spark to Falcon machine code. So if we were to execute our POC or productize any code on Falcon, you would need to use a tool called CCG, which stands for Common Code Generator, which would first convert Spark to C. And from C, we'll run our homegrown compiler to translate it to machine code. RISC-V, on the other hand, is public ISA and has native compiler supported by AdaCore, so we wouldn't need to go to such a step. So what is this Spark that we all have been raving about? Spark is actually a programming language as well as a set of tools. From the language perspective, it's a very large subset of Ada programming language. Ada is a full-fledged programming language similar to C, has all the same capabilities. When it comes to Spark, there is reduced functionality, but the most notable one is really just the reduced flexibility on the usage of pointers. This helps eliminate the aliasing problem that can be created by the developers. From the perspective of programming language capabilities, the paradigms are very similar to C and C++. Spark is an imperative programming language. You can write procedural or object-oriented code, and there are a few other facilities for programming in the large. In addition to those typical language capabilities, there is a particular capability that Spark has, which is not found in most other programming languages. And that's what really sets it apart. And that is the ability to specify program requirements within the code itself and use the associated set of tools to ensure that the implementation matches the requirements. Essentially, you are proving your programs, and that's a very powerful capability. And thanks to the design and subsetting of Ada, there is no undefined behavior in Spark. Spark comes with a set of built-in checks, and on this slide, I'll show a very quick example of what Spark can do at its very basic level. This piece of code is very simple, where the developer is just multiplying two numbers, X and Y, dividing it by a third number, Z, and storing the result in an array element. So how many problems can there be in this one line of code? Well, to begin with, the index could be uninitialized, and X, Y, and Z could also be uninitialized. But is that all? Not really. Index could be out of bounds of the array. The multiplication of X and Y could potentially overflow. You may have a divide by zero problem. And the final result of multiplication followed by division could be out of range or overflow. There are a lot of possible problems in just one line of code. And while many of us can stare at this code for some time and find all of these problems, when we have 10,000 lines of code or 1 million lines of code, it becomes increasingly difficult to be accurate and identify all the possible problems. But Spark doesn't really stop at just the basics. It has support for advanced verifications. In particular, it has two concepts called preconditions and postconditions. Preconditions help us define what are the conditions that need to be true before a particular subprogram. Subprogram in Ada or Spark speak is equivalent of function in C. And subprograms are of two kinds, procedure and functions. So preconditions help define what is the list of conditions that need to be true before a subprogram is called. And postconditions help define what are the list of conditions that should be true after the subprogram has been executing. So let's look at a simple example of a precondition. In this case, there is a procedure called next, which accepts an array. Unlike C, the order of arguments and the type is swapped. So A is the name of the array, and array type is the type of the array. An iterator is an integer which is supposed to be an index into the array. Typically, when we write a C code that takes in an array and another parameter which would be used to index into the array, we would be immediately writing a defensive code which checks that the iterator is within the bounds of the array. In Spark, we can just replace it with a simple precondition which states that iterator is in the range of is index. Now, what does that mean? Well, first of all, we don't need to carry the runtime check, so it saves space. Additionally, as security practitioners, we would love to force developers to add those defensive checks. And that's because we are never confident that, the program, even if there was no real situation under which iterator would be out of the range, we would never be confident and we would always like the developer to do it. But that has consequences. For example, that leads to additional code. It's less efficient code. But not only that, the developer needs to figure out what to do when the condition fails. And that's not always easy. And once they have written that code, they now need to write the unit test to test that code that they have written. They have to simulate this error condition artificially, which may be very, very difficult to simulate. With Spark, we can get rid of all of that. It's much more efficient code, and we have higher confidence. I was referring to post conditions earlier. This example demonstrates that. And post condition could also be used to check the implementation of the subprogram against the specification of the requirement. So this is a procedure called perform critical operation, and this procedure is expected to acquire a mutex. However, the caller of the subprogram may or may not have acquired the mutex already. So there are two situations. If the caller has already acquired the mutex, the callee, which is perform critical operation, should not acquire the mutex. Otherwise, you deadlock. And if the caller has not acquired the mutex, then perform critical operation can acquire the mutex, but it had better release the mutex before it returns. And this simple condition up here, mutex.isTaken, is a variable which tracks the current state of the mutex. And we are just saying that the tick old, meaning the state of this variable before this procedure was called, is same as the state after this procedure is done. In addition to the pre and post conditions, Spark has a facility called ghost variables and functions, which can be used to write even more advanced verifications. Let's first try to understand this example, and I'll cover what ghost is later. In this case, we have a procedure called move protection region. And move protection region is all about relocating a protection region from the from portion to the to portion in memory. So the green box indicates a large piece of memory. And within that, we may have a protection region, which is currently located here in the from portion, and we are relocating it to to. This is a protection region, and by protection, I mean it contains confidential data. In this case, we are moving the blue and the pink to pink and the orange. So pink is a shared part, which was part of both the from and the to. But blue, which was part of the protection region, would no longer be part of the protection region after it has been moved. That means if there was confidential data within it, it had better be erased before we relocate the protection region. With that, let's look at what this code is trying to do. The post condition says, let's scan all the bytes in the entire memory range. And the interesting portion is just the list of bytes that are within the from, and that's what this line says. However, if it's the pink portion, we don't really care about it. It doesn't need to be erased, which means we have identified the blue portion, and we are saying the blue portion should be erased. And if it is the green or the orange or the pink, it should not be erased. So what's the additional facility that Spark is providing compared to the previous slide I showed? Imagine this memory is, let's say, 4 gigabytes worth of memory, and we use a single bit to track each bit. That would be 4 gigabits worth of storage. That would be simply impractical to write code against. So this memory is an array, which is actually a so-called ghost variable, which will be used only in the context of program verification. When you compile your program, it ceases to exist. Next, I will talk about the alternatives to Spark and why we decided to not pick all of those. However, in order to appreciate the technical arguments, it's important to understand our motivation as well as constraints that we had that led to the decision. As you may have already inferred by now, security was our primary motivator. With respect to security, we are looking for something that would make a major difference to our security robustness story. The existing tools and techniques that we have been using, such as static analysis, compiler hardening, and fuzzing in certain cases, weren't really sufficient to move the needle enough. And we were really desiring to put certain class of problems, certain CWEs or common weakness integrations to rest for good. While we were using these techniques that I listed, like static analysis, over and over again, the problems would keep recurring. So there was no end. And we are looking to put at least some classes of problems to the rest for good and never have to worry about them. And then, as Daniel mentioned, the human factor was not scaling. Humans get tired as the number of line code increases, and we can't hire enough of them. We also had certain constraints that we need to respect before we could move from evaluation of Spark or the POC of Spark to actual adoption. In particular, by the time we finished our POC, NVIDIA had already started the journey to safety certification. That means if we adopted a new methodology, the immediate requirement that would arise is to make sure that the new methodology doesn't slow us down in our safety certification journey. And whenever you adopt any new tool or language, it's pretty much implied that there will be some sort of slowdown, which means it would be desired to ensure that, if we adopt something new, it helps offset the slowdown a little bit. For example, it cuts down the effort on safety certification, or it ticks more checkboxes in the ISO spec so that it makes a more compelling story. And lastly, none of the above would matter if the new mechanism was not going to be acceptable to NVIDIA safety assessor. Some more constraints. While there are a lot of tools out there already for foul methods and proofs, we were looking for something that could be used by everyday NVIDIA engineer. And as I mentioned in a previous slide, we also had a Falcon target to look at. And if we use Spark, a new programming language, and NVIDIA is forced to write a compiler for Spark, that would be pretty much impractical right there. You would also be looking for a very good support system because unlike C, Spark is not so widespread in community. So where do we get our help? And lastly, anything that we adopt should not add any unreasonable runtime burden. For example, it should not slow the execution of the code significantly or should not lead to a significant rise in the memory footprint. NVIDIA's security process in certain cases are very memory challenged, and a substantial increase in the memory footprint would have killed the entire project. With that background, let's look at the alternatives and why they didn't work for NVIDIA. The most leading alternative was FramaC, which has nearly all the same set of capabilities as Spark, at least on paper, which means you can demonstrate absence of a certain class of vulnerabilities. Henceforth, I'll use the term AORTE, or absence of runtime errors. And FramaC can demonstrate that as well. FramaC can also be used to model program requirements, the preconditions and postconditions that I showed earlier, and it is C. So to start off, it looks even better than Spark. But wait, it's not really C entirely. You have to learn the so-called ACSL, which is the specification language, which is the biggest benefit of it being C. Furthermore, it's not that you can just learn ACSL, write it, and get your program proven. At many times, the program would have to be refactored to be prover-friendly. And then C means inherently a weaker type system. For example, you cannot specify the range of a variable, which makes it much more difficult to do the exact same thing in FramaC compared to Spark. And it's also more time-consuming. Lastly, and which was probably the single biggest item that would have single-handedly made it difficult to adopt FRAMA-C was the commercial support. There was only a partial commercial support for FRAMA-C at the time we evaluated it, and which means there was no chance of safety certification. Rust was the next major alternative, not as good as FRAMA-C, but I'll still cover it. Rust has a very active community. It is a very loved language. It is memory-safe language, helps avoid data races as well. So it's a pretty good language, and in certain cases, it would be the right tool as well. But it does not address many classes of vulnerabilities that Spark or FRAMA-C would. And it does not offer any ability to write user contracts, which means it has just built-in constructs, not necessarily offering the flexibility to the user to do what they want in terms of writing program requirements. And based on a paper that I read, it's called the Wookiee paper, Rust has a higher memory footprint, and the Wookiee folks actually rejected Spark with one of the reasons being the high memory footprint. As I mentioned earlier, NVIDIA security process in certain cases are very memory challenged. So that immediately ruled out Rust. Rust also does not have formalized spec till date, and there is no commercial vendor, which means, once again, safety certification was going to be a problem. There were a few lesser-known alternatives, in particular Ivory and Verifiable C. Ivory is substantially different language compared to C. So the main charm that would be associated with a C-like language doesn't exist with Ivory. If you have to learn a new language, why not Spark? Why Ivory? Or it could be the other way around too. However, the next data point, which is the lack of enough commercial support, as well as the fact that Ada and Spark had been gaining traction, whereas Ivory seemed very limited, made it a very easy choice. I'll spend most of the remaining time talking about the POC, some of the concerns that arose along the way, as well as after the conclusion of the POC and our findings on the POC. POC with NVIDIA was a 3 to 4 month exercise, so we couldn't have possibly explored all possible areas of the language, support, and drill deeper into every aspect. So for POC, we had to restrict ourselves to a smaller set of goals compared to what we would have liked from Spark and the support system. First and foremost, we wanted to make sure that we can understand the language sufficiently and the usage of the tool chain. At the same time, we wanted to make sure that it is not too difficult for others at NVIDIA to learn and adopt. And once we are past that stage, we wanted to make sure that there is enough return on investment. And I talked about AORT earlier, and that's actually a very high degree of assurance. So at times it would seem too good to be true. Maybe the catch is that the engineering costs required to get to AORT is too high. And we wanted to make sure that we can get to AORT within a reasonable time frame and with a reasonable cost. And lastly, evaluation of the support system. As I mentioned, we couldn't have possibly evaluated.
AORT, absence of runtime errors, for those who aren't tracking the acronym.
Thanks, Daniel. Lastly, we wanted to evaluate the support system. As I mentioned, we couldn't have possibly gotten deeper into every aspect, so we wanted to make sure that if we find a problem after the POC was over, then we are in good hands. We also wanted to evaluate the runtime overhead of the language, but we couldn't really get to doing enough during the course of POC. We still continue to evaluate the code load and the performance-related aspects. So what are the code bases that we used during our POC? We used two applications. First one was a bare metal application, which acts as a root of trust for code running on several other security processors. And second one is a case of an application running under an RTOS, which handles the resizing of protection regions. You may have rightly guessed that the previous example that I showed with Ghost code was exactly from this POC. As I mentioned, there have been concerns. Concerns continue to arise, and I have tried to list some of the common ones that I expect many other people to also encounter. First is I can't find examples on the internet. It's a very true concern. Not all tools support ADA, and this would be very, very relevant in context of safety because safety requires us to use safety qualified tools. And we couldn't really just use just about any tool. It's difficult to find trained engineers. And if we are starting out to solve a problem of lack of sufficient engineering expertise, and then we make it further more difficult to train engineers, it wouldn't really work out very well. Some people would have concerned that they already have a lot of code out there. Then you already mentioned that Spark interfaces nicely with C. The proof messages are oftentimes difficult to understand. And sometimes you may want to pull your hair out because you could see that this variable is 0, but the prover can't see it's 0. And as I mentioned earlier, the code size may increase. But it's not that the concerns didn't have any solutions or at least mitigations. So if you can't find examples on internet, we have support services available through AdaCore. If you can't find tools, once again, look at the AdaCore tool suite, and maybe there's an answer there. Now, AdaCore is one company, so they may not have all the tools, and we actually did run into one such issue, in particular the code coverage tool. Thankfully, Ada has been around since such a long time. We were able to find a code coverage tool that suited our need from a different company. If you can't find engineers who know Ada, then we have in-house training available by now. And as already covered, C can be interfaced with Ada and Spark. So if you have a lot of code in C, that's not really such a big problem. You can take portions of code and convert only portions to Spark. If the prover is getting too difficult to understand, once again, we have in-house expertise developed by now. In fact, in addition to that, over the course of last 1 year, AdaCore has dramatically improved the quality of the error messages from the prover, which makes it so much easier to understand what's going on now. And while the code size increase is real, and in certain cases, like the CCG example, the case CCG, once again, is the tool that converts Ada to C that we use for our Falcon processors. In certain cases, it generates code that are language mandated checks that cannot be stripped out. There are compiler switches that can help us manage some of the code load. So there is no silver bullet here. There is a cost to adopting Spark. In the end, everything has to be traded against the return that we are getting on our investment. So what were the conclusions from our POC? From a security perspective, as I mentioned, we ran 2 POCs, 2 code bases, and we were able to write nearly all the code, convert all the code from C to Spark, which means there is going to be a fairly major impact to security robustness. The reliance on humans could be lessened thanks to the soundness of Spark and the ability to write user contracts. User contracts are those pre and post conditions that I showed earlier. Safety-wise, actually, safety was not a target during POC. It was a target that arose after POC, but before adoption. So safety-wise, Spark ticks more checkboxes in the ISO spec compared to, say, C. And coincidentally, Spark is completely acceptable to our safety accessor. In fact, it is preferred to our safety accessor as long as developers have sufficient training. And as I mentioned earlier, we have in-house training by now, so that's not a problem anymore. It can be safely mixed with C. We talked about mixing with C, but in this context, I'm referring to the fact that in a safety context, is it okay to mix Spark and C? And the answer is yes, it can be safely mixed with C. And throughout my presentation, whenever I use the term safety or safely, it is referring to ISO 26222 spec, which is for auto. For NVIDIA, from a safety perspective, Spark may not have made any difference to the effort, at least the first time effort that we are going to be spending on safety, because there's engineering costs associated with ramp up and the discovery of the new tools, trying to do different things. And these would offset some of the benefits of Spark. But in the end, effort neutral is still a great story because we are getting security benefits. And the hope is that in future, the savings on Spark will continue to repeat, whereas the one-time effort will disappear. Thinking practically, Spark is very practical to be writing code in. As I mentioned, we were able to convert nearly the entire code base from C to Spark. The support system is fairly world-class. We can actually count on AdaCore to answer our questions with a very low latency. AdaCore appears very focused on solving customer problems first. And lastly, from a performance or memory perspective, we do need to plan for some additional memory. As I mentioned, there are compiler switches to help, but sometimes hand operations may be necessary. And sometimes there may be no good solution, like I talked about the CCG case, so we need to plan for some additional budget. I'll end my presentation talking about the Spark benefits and the NVIDIA summary. First one is if it proves it works. This is directly a quote from two of our developers. The typical Ada saying is if it builds, it works. We have changed it to if it proves it works. And if it works most of the time because of the proof, that means there is less effort that's going to be spent during debugging. Developers also become quality engineers. That's a rather interesting one and a non-obvious one. With Spark, or at least the way the Spark and the toolchain is set up, developers get immediate feedback. When they write code, they get feedback immediately from the provers. And if you keep making the same kind of mistake a few times, at some point in time, you will learn and you will stop making those mistakes. Furthermore, when I observed on myself going from writing code to Spark code, I realized that as I was typing Spark code, I would think about what the prover would think. And I would have far fewer chances of hitting prover problems as I became more experienced with Spark. Now, you may call it, the fear of the prover, but in the end, it has ended up changing the mindset when writing the code. Which means now if I go back and write C code, I may not even necessarily need the prover to help me. It has changed the mindset. There is no Mr. C overhead. This is actually the critical benefit of Spark when viewed in a safety context. Numerous CWEs are put to rest. We talked about AORT, or absence of runtime errors, which covers things like buffer overflows, which is CWE 120, which would be put to rest for good. And now that all those classes of problems are simply not there, thanks to the prover system, reviewers can spend their time on other problems and not on the problems that a machine can solve. Here's the summary. Spark is now used for NVIDIA safety and security critical firmwares. The software, safety and security critical software, is expected to be productized in next year, mid or late next year. The scalability concerns around humans have been very nicely addressed by Spark. However, as I covered earlier, it's not entirely free of challenges, so I highly recommend picking the targets wisely, evaluating your return on investment, compare that to the cost associated, and you should have a good choice. I'm done. Thanks, everyone.
Same to you, Daniel. Thanks, Dhawal. Again, Daniel, same to you. Great presentation. I'd like to move into the Q&A section now. Dhawal, just a quick aside. I believe you were actually convinced to move into Spark as well, right? It had to take you some as well.
That's right. So the very quick history is that when Daniel forwarded me an email from AdaCore asking me to look at Ada, I immediately rejected it. And then he was confused, why am I doing so? And then he said, go look at this thing called Spark. And when I looked at Spark, my eyes started lighting up because it almost felt too good to be true, something I have never seen earlier. And so, I started converting over. However, as I mentioned earlier, a POC was required to gain more confidence.
Right. That's a big deal, yeah.
I'll comment, he's not the only one. There have been others that, as we've engaged through this process, that have been detractors. that have subsequently become champions once they've sort of gotten in it and gotten past the initial inertia of, hey, this is the way we've been doing it the last 20 years. It's been transformative for those who've really taken it seriously and looked at the challenges that are facing us and were willing to take it head on.
We have a bunch of questions coming in, but I do want to maybe ask a couple of quick generic questions too as well before we get into specifics, right? What would you suggest for anybody trying to make this big shift? I mean, like you say earlier on, Daniel, it's heretical almost to say that let's not use C, let's use Ada or Spark, right? What advice would you give somebody? Now, you addressed some of those issues earlier on, right? But offhand, from your own experience, what would you say?
I mean, I think, because it is heretical and it certainly takes some daring, you should definitely prepare to make both the business and the technical argument. You really have two audiences to overcome inertia of this. Hey, this is the way we've already been done. Both are doable, but you need to understand the concerns that each of those groups are going to bring to bear on the question and be able to address those forthright. Dhawal talked about code bloat and speed and performance. Those are technical concerns. How do you operationalize that within your build infrastructure? Your operations guys are going to have some questions. And your business folks, like how much is this going to cost? Is it going to slow my schedule down? All of those things will be real concerns. We found internally we could keep, for the most part, things cost neutral, schedule neutral, when we were tactical about where we engaged. And I think that is sort of the key. It's a new tool in your toolbox to be applied to certain types of problems. It is not the tool that you shouldn't rewrite a 10 million line of code operating system this way, or at least I wouldn't recommend it based on where we are today. But there are definitely code bases where this has enough return on investment that it's worth, training up new skills within a core set of engineers to go after it, for sure.
So the goal, I guess, the priority is to keep it small and keep it tight starting out, right? Keep it close.
Especially for something that is antithetical maybe to your internal culture that may be very entrenched in a C view.
How will this first be instantiated by NVIDIA, right? How will it first appear? Will it be in upcoming chipsets? Will it be in upcoming firmware? Can you elaborate upon that quickly before you answer the questions?
I think Dhawal talked about it, late next year. We're sort of disinclined to speak to future product roadmap.
Right.
But, it being software, it could show up in any of our verticals at any point when it's ready. And to that end, adding this tool to our arsenal, I think our goal is to migrate over time. So even products that are already in the field today likely will benefit from this in time as we reinvest in various firmwares and low-level kernel components that we migrate over in time. So I expect you'll be seeing it in products near you in automotive and GPU and data center across our product space.
Okay. We have some quick questions to get to quickly. So working backwards from Glenn, how much training time and support did you need to become productive? Do you reckon? Give it a quick estimate, I guess.
I think that's best for Dhawal.
Sure. We started with 1 week training. However, the 1 week training wasn't really entirely sufficient to cover all aspects. Now, at this point in time, I would say if I were to rewrite the training, probably 1 week training would be sufficient. Now, 1 week training is just the training part, and then there's ramp-up part because engineers need to try and get their hands dirty and, learn. If you just keep listening to the presentation, that doesn't really sink in. So I would say combine 1 week of training and 2 weeks of, trying it yourself to get comfortable. That may still not be sufficient because you will almost definitely find things that you didn't know, how you need support. So there will be some cost, small cost as you go along. But I think with 3 weeks, you will be in a fairly well positioned to start coding.
Okay. And from House Silva, go ahead, Daniel, got a quick comment on that?
Yeah, I was going to say that there are also ways to, we paid some recurring costs of having engineers, learn how to encode registers and things. And as we move forward, we're encoding some of that knowledge in libraries and other things that others can leverage that they don't sort of have to reinvent on their thing. And that's really just building out our own internal ecosystem. So as you go farther down this path, this scales better for subsequent engineers. But that first startup cost is going to take a little time.
Okay. One quick question from Scott. How does pre- and post-condition scale to inputs that are hardware generated? For example, hardware failure causes a value to go out of range. How would you address that?
That's a wonderful question, actually. We do actually use it in certain cases, and the way it works is we use ghost code. So what happens is, if the hardware is changing asynchronously, the programming language will know about it. But if, let's say, it is changing synchronously within the flow of the program, then what you would do is you would have a ghost variable that reflects the state of hardware. And when the hardware is updated, you would update the ghost code state within your code intentionally, deliberately, to reflect the hardware state. And from there on, the pre and post conditions would work just like it was all software state.
Right. And one more good one from Scott, right? Yeah. Give me a quick second here. I lost it again. Okay, they're coming in fast and furious. Has the, this is from, Scott, I found him again, okay. Has the Spark 2C compiler been proven correct?
There were some challenges initially, yes, we found problems. But over the course of time, it has stabilized and is working fairly well for us.
And they were using Spark 2005 or 2014. And again, keep in mind too, I guess, maybe a quick comment on how this and that were our granny's Ada, right? So maybe we comment on that too.
Correct. We are using Spark 2014.
Yeah, it's much like C99 isn't, modern day C++. Ada has come a long way since the 80s, even 2000.
Here's a quick good one from Matthew. Did proving pre and post conditions on the Spark code cause you to discover previously unknown bugs in the original C implementations?
Absolutely. We discovered numerous problems. We had, in the first POC that I talked about, which was the root of trust, there were multiple off-by-one problems. And not just that, there was a fundamental architectural API-level design problem which would have prevented one of the corner cases inputs to actually even be sent down. So yes, it does help.
I think we're running up against the clock here, guys. One last one. And now keep in mind, too, that we'll be able to provide the answers to follow-up questions on the webinar afterwards, right? So feel free to ask more questions and we'll answer them offline afterwards, right? So what is the MISRA C overhead? Any quick comment on that?
Definitely. So the way NVIDIA performs MISRA C coverage is we use a tool called Coverity. And on any substantial code base, let's say 20,000 lines of code, when we run MISRA C, we end up with 20,000, 30,000 errors. That's very impractical for humans to go through each of them and determine whether we should actually do something with it or dispose it as false positive. So MISRA is very pedantic spec. And consequently, there are a huge number of warnings to deal with. And the effort to dealing with these warnings is what is substantial around MISRA C.
It's effectively trying to use humans to manually do proving of like integer overflow and things, which just gets really difficult, and not good use of human brain power. Tooling like the provers in Ada are much more effective at answering the questions MISRA is attempting to assert through spec.
I think lots more questions can be asked on that one, right, and answered offline. Listen, guys, great job today. I really appreciate it. Great overview on what's happening here. So with that, I'd like to sign off. This is Patrick Mannion with Daniel and Dhawal, and we'd like to hand it over to our support team. Tim, over to you.